Prepare to be swept away into the enigmatic depths of the cosmos as we unravel the captivating mystery of pulsars. Brace yourself for a cosmic symphony of unimaginable proportions, where stars become cosmic lighthouses, emitting precise pulses of radiation that defy the boundaries of our understanding. Join us on an exhilarating journey into the heart of these celestial enigmas, where gravity warps, time distorts, and the universe unveils its most mesmerizing secrets. Get ready to explore a pulsating universe that dances to the rhythm of its own mysterious beat. Pulsars. Pulsars are rapidly rotating neutron stars that blast out pulses of radiation at regular intervals ranging from seconds to milliseconds. Pulsars have strong magnetic fields that funnel particles along their magnetic poles, accelerating them to relativistic speeds, which produces two powerful beams of light, one from each pole. According to the University of California, because the poles of the magnetic field aren't aligned with the axis of spin of the pulsar, the beams of particles and the light they produce are swept around as the pulsar rotates. The periodicity of pulsars is caused by these beams of light crossing the line of sight here on Earth, with the pulsar appearing to switch off at points when the light is facing away from us. The time between these pulses is the period of the pulsar. How do pulsars form? Like all neutron stars, pulsars are born when stars with masses between 4 and 8 times that of the Sun run out of fuel for nuclear fusion, says Penn State University. When the fusion of lighter elements into heavier elements stops, the production of energy that supports the massive star against the inward pressure of its own tremendous gravity also ceases. The balance the star has enjoyed all of its life ends, and it begins to collapse. As the collapse proceeds, the outer layers of the star are blown away in a supernova explosion, with only the iron core of the massive star containing masses equivalent to that of the Sun up to about 1.5 times that of our star remaining. This crushes down into a width no greater than around 12 to 17 miles, 19 to 27 kilometers, around that of a city here on Earth, according to NASA Goddard. This creates neutron star matter composed of 95% neutrons, because the collapse has forced electrons and protons together. According to NASA, the material that comprises neutron stars is so dense that a mere teaspoon of it would weigh 4 billion tons. This is equivalent to 10,000 Empire State Buildings stacked on a tiny spoon. Are all neutron stars pulsars? In short, all pulsars are neutron stars, but not all neutron stars are pulsars. The majority of neutron stars we have discovered thus far are pulsars, but that's because they are far more obvious than neutron stars. With large beacons of radiation blasting out from magnetic poles, astronomers can observe these cosmic lighthouses far easier than small, dim neutron stars. However, some pulsars may not be observable from Earth because their radiated beams of light don't ever orientate themselves toward us. We can be fairly certain that pulsars are rapidly spinning neutron stars because young pulsars have been detected within the remnants of supernovas, exactly where neutron stars are expected to be found. Other neutron stars that currently don't appear to be pulsars and look like non-rotating neutron stars may have once been pulsars, but the process that causes them to blast out beams of radiation may have turned off, or the emissions may be too weak to be observed. The average lifetime of a pulsar is around 10 million years, and as they age, their rotation slows. W2 discovery the pulsars. Following the discovery of neutrons in 1932 by English physicist James Chadwick, the concept of a neutron star was first predicted in 1934 by Lev Landau in the Soviet Union and separately by Walter Baade and Fritz Zwicky in the U.S. during the same year. 5 years later, in 1939, Robert Oppenheimer and George Volkoff would develop a theoretical model for neutron stars, but it would take a further 3 decades for the first neutron star in the form of a pulsar to be discovered. In 1967, radio astronomers in Cambridge were involved in the search for quasars and had developed an instrument capable of detecting rapid and random changes in the intensity of radio waves that saved such signals for later analysis. Pulsar extremes. How fast can pulsars rotate? Like all neutron stars, pulsars have quite tightly constrained masses and sizes. Most neutron stars have a mass of around 1.5 times that of the Sun. One respect in which pulsars vary a lot is their rate of rotation. Some spin at a rate of hundreds of times per second, which NASA says is faster than the blades of a household blender. In 2022, astronomers discovered the heaviest neutron star to date with a mass of 2.35 times that of the Sun, which is also the fastest rotating pulsar ever found in the Milky Way. The pulsar designated PSR J09522607 is also known as the Black Widow pulsar, as it is believed to have reached record-breaking rotational speed and mass by consuming a companion binary star. The Black Widow pulsar rotates at 707 Hz h2, or 707 times per second. This is topped by the pulsar PSR J1000, 748 2446 AD, which rotates at 716 Hz, or 716 times per second. Uses of pulsars. Pulsars are fantastic cosmic tools for scientists to study a wide range of phenomena. The light emitted by a pulsar carries information about these objects and what is happening inside them. That means pulsars give scientists information about the physics of neutron stars, which are the densest material in the universe, with the exception of whatever happens to matter inside a black hole. Under such incredible pressure, matter behaves in ways not seen before in any other environment in the universe. The strange state of matter inside neutron stars is what scientists call nuclear pasta. Sometimes the atoms arrange themselves in flat sheets, like lasagna, or spirals like fusilli, or small nuggets like gnocchi. Some pulsars also prove extremely useful because of the precision of their pulses. There are many known pulsars that blink with such precise regularity, they are considered the most accurate natural clocks in the universe. As a result, scientists can watch for changes in a pulsar's blinking that could indicate something happening in the space nearby. Pulsar vards. All pulsars slow down gradually as they age. The radiation emitted by a pulsar is jointly powered by its magnetic field and its spin. As a result, a pulsar that slows down also loses power and gradually stops emitting radiation, or at least, it stops emitting enough radiation for telescopes to detect, Harding said. Observations thus far suggest that pulsars drop below the detection threshold with gamma rays before radio waves. When pulsars reach this stage of life, they enter what's known as the pulsar graveyard. Pulsars that have stopped emitting may be considered ordinary neutron stars by astronomers. As we reach the electrifying conclusion of this enthralling expedition into the enigmatic realm of pulsars, we find ourselves humbled by the cosmic marvels that pulsate with the beat of the universe. These celestial lighthouses, with their mesmerizing rhythm and dazzling precision, illuminate the darkest corners of space, casting light upon the secrets of stellar remnants. Pulsars, with their mind-boggling speeds and immense magnetic fields, challenge the very fabric of our understanding, inviting us to question the limits of nature itself. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.